Welcome back, students. In this video, we're going to look at enantiomers in more detail. Enantiomers are a pair of compounds that are mirror images of one another. But what's special about them is when you put those compounds on top of one another, they don't coincide. So even though they have the same connectivity, and they're mirrors of each other, when you place them on top of one another, their atoms don't agree. They aren't pointing in the same direction. Below, I have a pair of enantiomers drawn, and I want you to visualize something for me. I want you to take the enantiomer that's on the right-hand side that I've boxed in yellow, and I want you to mentally pick it up out of the page and place it on top of the enantiomer that I'm boxing in blue. When you do that, what you'll find is this carbon and this carbon are agreeing with one another. This carbon and this carbon are in the same location. You keep going, this one and this one are agreeing, this one and this one are agreeing, but you know what's different? In the structure where we've boxed that in blue, the OH on the second carbon is coming out of the plane of the page. Whereas in the other structure, the OH is going behind the plane of the page. So even though every other part of this agreed, the two OHs are not pointing the same direction. They're on the same carbon. They're both on carbon number 2, but they're not pointing the same way. We call this non-superposable. Now, real quick, I want to remind you about what superpose versus superimpose means. Superpose means when you lay two things on top of one another, they coincide. Whereas superimpose is just put two things on top of one another. Who cares if they coincide or not? The problem is in about half of the textbooks, they're going to misuse this term. They're going to say non-superimposable mirror images, when what they actually mean is when you take these two enantiomers and you put them on top of one another, they do not coincide, which is technically non-superposable. In order for a compound to have an enantiomer, it has to have at least one chiral center. And now you might end up graduating to a more complex definition, but we're just going to keep it nice and simple for Organic Chemistry 1, at least as simple as possible. And then your enantiomer must not be the same compound. Now, we're going to talk about that a little bit more when we get into some examples. But in order for us to have an enantiomer, we have to have a chiral center. And when we draw the two enantiomers, we have to then double check to make sure that we haven't actually drawn the same compound twice, because that is possible in some situations. Let's talk about drawing an enantiomer. When you have a molecule that has a chiral center, you need to be able to draw its enantiomer. So for example, I'm just going to redraw the structure that I have down below and point out that if I didn't have a wedge bond where that NH2 was, if I just had a plain bond, that we could put the asterisks here to show that that's a chiral center. And we want to be able to draw both enantiomers for that compound. When we're drawing enantiomers, remember that these molecules are mirror images of one another. So we need to start visualizing where are we going to put the mirror when we draw the mirror image. And there's several locations, and we're going to talk in detail about two of them. So one location would be a mirror to the left or the right. So where I've drawn this blue line, there could be a mirror there. This one's hard to draw, so I'm going to draw it in highlighted blue, but you can have a mirror kind of behind the compound. So this would be my mirror that I'm trying to illustrate in blue highlighter. And then you could also have a mirror above or below the compound. So you could have a mirror down here. So imagine that you have a molecule and you have three sides of a cube around that molecule. Those are all your potential mirrors. Most students find it easier to either look for a mirror or draw a mirror, either to the left or right of the molecule. And then also the other way that students feel more comfortable is when they draw a mirror behind a molecule. Most people don't draw the mirror above or below. Let's look at the locations where we can put the mirror and show how we would start with this molecule and how we would get its enantiomer. Let's pretend that we've drawn a mirror behind this molecule. So I'm going to draw in just kind of like a box and then remind you that the mirror is behind this molecule. If the mirror is behind the molecule, what happens when we draw its mirror image is the carbon skeleton ends up staying the same. So we are projecting the carbon skeleton in the same fashion. Meaning that we're not changing, that the benzene ring right now is on the left, it's staying on the left. Once you get to the benzene ring at this position, right, your NH2 is there, that's staying there. So we're keeping the skeleton the same. And then the directionality of the wedge and dash bonds flip. So here that NH2 is on a wedge bond. In my mirror, it will now be on a dashed bond. So this would be if you had your mirror behind your molecule, or technically could be in front of your molecule. What if the mirror was to the side? How would that change? So let's pretend we have a mirror here. In this case, your carbon skeleton flips. So when your mirror is here, I'm going to mimic what I see on the left-hand side over on the right. So I'm looking at this structure and I'm just mimicking the direction of these bonds. Now, because I've mimicked this, the direction of the dashed and wedge bonds actually stays the same. So my mirror to the right or to the left is going to keep the directionality of the wedge dash bonds being the same. And what's going to change is the carbon skeleton is going to flip from, the phenyl, the benzene ring on the left, and now it's going to be on the right. So these are the two easiest places to visualize a mirror. It's not easy. It's going to take a lot of practice, but usually you need to kind of pick one, start with it, and start practicing drawing enantiomers, choosing the mirror to be either behind your compound or to the side of your compound. I want you to take a moment and draw the enantiomer for the following compounds. You can choose your mirror to be to the left or to the right. You could choose it to be behind, whatever your preference is. Note, I do have some tricky ones in here. So we'll come back and talk about them when you're ready. Let's compare some answers. For this first one, what I expected you to do is to see this wedged NO2 and think, oh, there's a chiral center there. But you know what? There's not. This is a super classic issue where once we start drawing wedge and dash bonds, students start seeing chiral centers where there isn't one. A student will see a wedge bond and say, that's a chiral center. Not necessarily. There needs to be 4 different groups attached in order for us to have a chiral center. So this compound, if I were to draw its enantiomer, which I purposefully said enantiomer in quotes, because it doesn't have an enantiomer. And this is an example of what I was talking about at the beginning, where if I draw its enantiomer and the enantiomer is really the same compound, then these are not enantiomers. How do I know this is the same compound? Well, what I'm visually doing is I'm going to be taking the so-called enantiomer, and I drew a green line through it to show an axis. And I'm going to rotate around that axis 180 degrees. So right now the NO2 is going behind the plane of the page. When we rotate 180 degrees, then what will happen is the NO2 will be coming out of the plane of the page. And so the NO2s are going to agree. And because this group is the same as this group, then those already agree this is not an enantiomer. There's no chiral center here. This is just a really common trick question. I apologize, I started you off with a trick question. So this one has no chiral center. So there's no enantiomer. Let's look at the next one. This one's tricky because there are actually two chiral centers here. And I'm going to draw my mirror as if it's behind. So we'll start with that. So if I'm drawing my mirror as if it's behind the molecule, I'm keeping my ring in the same location. I'm keeping the substituents coming off at the same location, but I'm switching my wedges to dashes. And because I have two chiral centers here, right, one here and one here, I'm going to switch the directionality of both of those groups. So these two are enantiomers. Pretend instead of putting the mirror behind, you would have put the mirror next door or to the side. If you would have put the mirror to the side, then I'll show you the drawing of the enantiomer that you would have come up with. So if you put the mirror off to the side, so right here where I'm going to draw that dashed line, then you would have had this drawing as your enantiomer. So here's the key. Right, here's one enantiomer, and here's another enantiomer. Right, that pair is a set of enantiomers. If you didn't choose to draw the one I highlighted in blue, then you could have chosen the one that I'm boxing in blue. Right, so if we maybe label these as 1 and 2, these two that I've labeled 2 are the same thing. They're just looking at it from different perspectives. So you draw one or the other because a pair of enantiomers is just a pair. Then the final one probably tricked your eyeball as well. I bet you looked at this and said, chirality center, chirality center. No, it's not. It's not a chirality center because you know what? You have a CH2 here, CH2 here, OH here, OH here. Sorry, it's not a chiral center. Let's change it a little bit to actually make it a chiral center so that we can get some practice. So this one's just like the top one where this one has no chiral center, so there's no enantiomer. But if we change it, we can make it into something that does have a chirality center and thus does have an enantiomer. So I'm going to erase one of the OHs. Give me a second. All right, I erased one of the OHs, and now there are definitely 4 different groups attached to the carbon that is starred. Now you can draw the enantiomer of this. Most students, honestly, they really, I think, like to put the mirror behind the compound. That's where people do the best. Now, there is something that goes on for this particular example where people get a hair confused. So let's go ahead and draw out the carbon chain. And then I can never remember which way my students like and which way they don't, so I'm just going to show you both and tell you that they're the same thing. So the dashed bond can have the CH2OH on it, and the wedge bond can be the CH3. So that's one way to draw this structure. The other way, still with the mirror behind, would be to draw, like it. All right, I think it's like this. I think that if my memory is right, the way that I like to do it is this way, and the way that my students like to do it is the first way. I think that my students like to keep the direction that the wedges and dashes are pointing the same, and they like to change the location of which groups are attached. But really, the two compounds I've drawn here are the same. One of them is if you look from this way, and the other one's if you look from this way. So it's just a perspective thing. It doesn't matter. They're the same compound. Do what makes you feel happy. So again, because the two that I've drawn are the same thing, you would draw one enantiomer and then you would pick one of the two that we've drawn here. So maybe you pick this one, and that would be your set of enantiomers. Here, I want you to do another example. I want you now to be given two compounds and you to tell me what the relationship between those compounds are. So are they enantiomers, are they constitutional isomers, or are they the same compound? So look at these four pairs and decide what the relationship is, and when you're ready, we can come back and we can compare. All right, let's look at the first one. For the first one, what we're seeing is somebody drew a mirror here and they generated the other compound. When you do that, you just need to double check to make sure that those two compounds aren't the same that you've drawn. And the way that you're going to do that is pick one of the compounds, and I'm going to take this one and I'm going to rotate it along that green line. When I rotate this along the green line, what ends up happening is those dashed methyls, those dashed CH3s, will be in the plane of the page right now, and when we rotate it, they'll come out of the plane of the page. So really, these two compounds, these are the same compound. It might look like they're enantiomers, but because there's a plane of symmetry within that molecule, that allows us to, when we do that rotation, end up with actually the same compound. We're going to spend some more talking about that when we look at another type of stereoisomer called diastereomers. For the next one, you need to look at the same type of thing. Here we have a mirror, and we've generated that second compound. The difference between the first example and this example is that these two groups attached, they're not the same group. So if I were to take one of my compounds and rotate it to see if I can get the directionality of the bonds to agree with one another, well, then where each atom is located doesn't agree with one another. Because if I rotate that second molecule, what will happen is this bromine will now be on top, even though it's pointing outward, and that OH will be pointing outward but be on the bottom. And if I mentally take this compound and place it on top of that one, I see that even though the directionality of the bonds has been corrected, the location of the substituents do not agree. So these are enantiomers. These are non-superposable mirror images, right? They were mirrors, and then we tried to put them on top of one another. They did not agree, so they're enantiomers. Let's look at the bottom one on the left. In the bottom one on the left, what I want to point out is that we have kind of two things going on. First, if we imagined that we had a mirror here and we looked at the carbon skeleton is being mirrored as if we had a mirror to the right-hand side of this molecule. But in addition to that, we're changing the direction of the OH from wedge to dash. And that's a problem because what we're doing is we're mirroring both parts of your molecule. We're mirroring the carbon skeleton as well as the bonds that have a direction. And what ends up happening when you mirror both of those aspects is you actually just make the same compound. The way to generate or to confirm that is if I take my compound and I put in this green line, which is my axis, and I rotate around that axis and I flip it, what will happen when I rotate 180 degrees is now that pi bond is going to end up on the right-hand side, and the OH that was dashed is going to be now wedge. And would you look at that, these two are the same thing, which meant that the first pair of structures that were drawn are also the same. Finally, the last one, These are also enantiomers. These are enantiomers because we see a mirror here. And when we mirror this way, notice how the fluorine was wedge and the fluorine is still wedge. That's imperative when you have a mirror to the right. When you have a mirror to the right, whatever was wedge needs to stay wedge, whatever was dash needs to stay dash, and what changes is the direction of your carbon skeleton. So how I would confirm that these are non-superposable is I would look at the fluorine and rotate around this carbon. When I do that, my methyl is going to end up on this side, and the fluorine will be here at that second position, but it's not going to be wedge anymore because you rotated it 180 degrees. Now it's going to be dashed. If I take that fluorine compound and place it on top of the first one, they do not coincide. Beautiful. A lot of these had mirrors to the right, and I just want to go back to that first one and say that even though I drew that mirror right there, this was actually a mirror behind. It's just hard to draw the mirrors behind. You are definitely going to expect problems like this on your test, no matter who your teacher is, right? We're going to give you pairs of compounds and ask you the relationship, and as we learn more, the different relationships are just going to add to this. So as we continue to practice, you're going to be adding things like diastereomers to this list of potential relationships between compounds. Let's wrap up. In this video, we defined enantiomers and we looked at the different locations that we can draw mirrors. You want to be able to be given a compound and draw its enantiomer, but you also want to be able to be given a pair of compounds and determine what the relationship is between that pair, such as enantiomers, constitutional isomers, or the same compound. Thanks so much for watching. This is Katoni signing out.